So in this tutorial, I'm going to discuss about the time series ARIMA model. So far in this section, we have discussed what are the moving average model, what are the autoregressive models, and what are the autoregressive moving average model or ARIMA models. So the next in this series is the ARIMA model. So whenever we learn about time series analysis, we start with the basic the stationary model like ARMA and move on to how to handle the non-stationary cases, and that's where the ARIMA model is very useful. Okay, so let's get started. Alright, so let's do a brief recap what we have learned, and then we'll go on to study the ARIMA class of time series models. Alright, so what we have learned so far is the MA models. The specification for MA model is YT is a function of the error terms, okay, and that's the MA models. Okay, in the AR models, you've got the 2 days time series is a function of the previous data. For example, in an AR1 case, it's a function of or it's a linear combination of the previous period data, just one period sort, and it could be several lags, like it can have YT minus 1, YT minus 2, and so on. In the ARIMA model, it combines the MA terms and the AR terms. So MA terms come from the error terms, and the AR terms are nothing but the lag of the same series, right? When it combines, you get the ARIMA class of models, right? So that's what we have already learned in this particular series. Now, what are the ARIMA class of models? In fact, ARIMA, MA, AR, and ARIMA are some specific case of ARIMA class of models, and we'll talk about that later on in this particular tutorial. So let's see why there is what additionally should be done in order to consider the non-stationary case. Okay, so the above models that we have learned so far cannot handle non-stationarity, okay, or a particular series which has got a trend, right? So a series which is a trend is considered to be non-stationary, which has got the statistical properties of that particular series is not constant over time. What are the properties? The mean, the variance, the autocorrelation, and so on. So for a series to be stationary, these statistical properties like mean, variance, and all have to be constant over time. Okay, so here is an example of a non-stationary series. So we have got YT data, and you have data points here. When you plot it out, what we get is a series which has got trend. So you can see an upward series with upward trend. There can be a series with downward trend as well, right? So that's a non-stationary series because it's not reverting towards mean. One of the important aspect of a stationary series is that every time it goes up, it also comes down once in a while, so that it reverts back to its own mean or average value of the series. Doesn't happen over here. You can see a constant upward trend in this case, and that's simply growing. The mean is going up. Sometimes the mean will be constant over time, but the variance is not constant. Okay, so that can be a series something like this. Okay, well, the mean is constant, but you can see the variance is not constant. So that's also not a stationary series. Okay, so one of the way to handle or to make a stationary series non-stationary series a stationary is by differentiating or simply taking a difference of the same series from its lag. Okay, so let's do it. So we take the first difference. So first difference is nothing but YT minus 1. Okay, YT is the current series and the previous or its own lag is YT minus 1. When you take the difference of that, you get some sort of a numbers which if you plot these numbers, okay, we'll get a series which will look more like a stationary series, okay, and we'll learn later on this in this particular tutorial that it's not the first difference that's always required. Sometimes higher order of differences or differentiating will also require for a series to to be stationary, okay. So but one thing for sure is that when a series looks non-stationary, if you take a difference or simply you take you plot the difference between the yt or yt minus 1 or maybe the second difference, then it will look close to stationary, okay. So let's take an example, another example which will show you slightly interesting pattern, okay. So here is a series with us. We have got numbers like 25, 16, 9 and 4, okay. So can we see any pattern in this? Okay, so the pattern is that it's increasing. If you plot it, you will get, okay, something like this, right? Because it's increasing 4, 9, 16, 25, so it's ever increasing. So let's take the first difference of it. First difference is just the difference between the consecutive numbers. 25 minus 16 is 9, okay. So 25 minus 16 is 9, and then 16 minus 9 is 7, and then 9 minus 4 is 5. So this is the first difference I have taken. When you take the second difference, okay, second difference is don't confuse second difference like 25 minus 9, okay, because this is the second difference. That's not the second difference. Second difference is the difference of the difference. That means we have already taken the first difference. It's the difference of that. That means 9 minus 7, which is 2, 7 minus 5, which is 2. That means when we did or took differences twice, you can see the numbers are just same, right? Here in the first case, there was no pattern actually, honestly, when as in pattern, as in it looks like there is some sort of a variation or some sort of a trend. But when you do took difference twice, the numbers are just same, okay. So when the numbers are same, it has got constant mean, right? Because there's same numbers, so the mean is constant. Also the variance is constant. In fact, the variance is 0 in this case, right? And that's what is the impact of taking difference. So whenever you take difference of a series of number, you tend to be closer to some sort of a constant mean and variance. Not all the times, but if there exists some sort of an upward or downward trend, then it will happen. It may not exactly be the case in a real time series because the numbers will not follow such a pattern. But yes, just to do just to show you an example where it clearly you can see that taking a difference make a particular series with constant mean and constant variance. Okay, so that's what you can see here. Okay, so how did I get these numbers 25, 16, 9 and 4? Well, it's nothing but the function x square plus x plus 1. Is it 1? X square plus x. Alright, so it's x square plus 2x plus 1. 2x plus 1, sorry. Maybe I can use here. So it's x square plus 2x plus 1. Sorry. So when x equal to 1, fx is 1 square plus 2 plus 1, which is 4. When x equal to 2, it's 4, and then plus 1, which is 9. X equal to 3, then 9 plus 6 plus 1, which is 16. And when x equal to 4, it's 16 plus 8 plus 1, which is 25. Okay, so that's how I got these numbers, right? Now if you take the if you use calculus, okay, take the first derivative and second derivative of this function, what do you get? Take the first derivative, okay. So let's take the first derivative dy dx of x square plus 2x plus 1. So what do we get? 2x plus 2, right? And that's the first derivative, right? Let's take the second derivative of that, okay. dy dx of df by dx, okay. So let's take the second derivative, okay. So dy dx of 2x plus 2, which is nothing but 2, right? That means when you take take a second order polynomial, okay, x square plus 2x plus 1, and you differentiate it twice, you get a constant. If you take a third order polynomial, like let's say x cube plus 2x square plus 3x plus 4, if you take third order polynomial and you differentiate it thrice, you will get a constant, right? So the order of differentiating a function in order to get to a constant value or in some sort of a stationarity scenario will differ based on what is the polynomial in front of us, okay. Is it a second order polynomial, is it a third order polynomial, and so on, okay. So the stationary non-stationary series could follow sometimes one of these order of polynomial, okay. It could be second order, third order, and so on. And when you actually so what we can do is that we can use this same method, taking the difference in order to reach out to some sort of a stationarity, and then the stationary models can be applied, and then the forecasting can be done. All right. Now let's understand a bit about taking a difference, okay. So how do we take difference? Okay, how do we introduce difference in the ARIMA class of models? Okay, so we have the ARIMA previously. Now we have additional term which is I. So I stand for integrated. Okay. So when in the first, when there is no differentiation, okay, then the model, the differential model is exactly same as, or the difference series is exactly same as the one before differentiating, because there is no differentiating happening here. When you take the first difference, it's just the data for this period, current period, minus data for the first lag period. Okay, so yt minus 1. When you take second differentiating, d equal to 2 or I equal to 2, so the notation could differ. I'm taking d equal to 2. Some people take I equal to 1, I equal to 2, and so on. Okay, so when you take the second difference, it's not yt minus 2. Often people confuse with this. This is not true. Okay, so this is not second differentiating. What we mean by second differentiating is the first difference and the difference of that first difference. Okay, so take the first difference for yt, take the first difference for yt minus 1, and when you take the difference of these differences, so this is one difference, first difference of yt, first difference of yt minus 1. When you take the difference of this difference, we get this second difference, okay. And when you simplify it, you will get the second difference as this, okay. Second difference is yt minus 2, yt minus 1 plus yt minus 2, and so on. You can also extend this to third difference, fourth difference, and so on, and this will become more complicated. All right. So in the ARIMA class of model, you have got three terms. So in the ARIMA, we used to have two terms, the AR terms and the MA terms. We also know now the number of differentiating that is also part of the order of ARIMA. Okay, so there are P, Q, and R. Okay, so P stands for the number of AR terms, Q stands for the number of differentiation that is happening, and R stands for the number of MA terms, or the moving average terms. Okay. All right. So as I've said in the beginning, the ARIMA class of model is very general class of model. So we can derive the AR model, MA model, ARMA model from the ARIMA model. So ARIMA is pretty generic. AR, MA, ARMA are some sort of an instance or instance of ARIMA model. Okay, or special case of ARIMA model. Okay, so one such case is ARIMA 100. Okay, so P is 1, Q is 0, and R is 0. That means no differentiation is happening. There's differential operator order. There is no moving average order. Only there is the AR terms. Okay, so that's nothing but a AR model, right? Because Q and R both are not there. That means no MA terms, no differentiation happening here. Okay, no differentiation is happening. And then ARIMA 001, which is nothing but a MA model. Okay, because only MA terms are there. Auto-regressive and differential terms are 0. ARIMA 101, no differentiation happening, but both AR and MA terms are there. So that's nothing but the the ARMA model. Okay. Hence, these models, AR, MA, and ARMA models are the special cases of ARIMA model. So that's why it's called a general time shape model. All right. There are more aspects to it also. We've talked about the random walk model. Okay, so random walk model is also is a special case of ARIMA model. So when you have the AR term is 0, the MA term is 0, and only there is first difference of series, then it's random. It depicts a random walk model. Okay, so random walk model is nothing but is some kind of an AR model where the coefficient of the first lag is 1. Okay, now for in typical AR model it is always less than 1, but in random walk model it is 1. Hence ARIMA 010 is represents the random walk model. Okay, all right, because the first difference if you see the first difference yt minus 1, there is no AR term, there is no MA term, there is only a constant. And if you take the yt minus 1, which is lag, to the right hand side, it becomes yt equal to yt minus 1 plus a constant term, and that's nothing but a random walk model. So a random walk model is also a special case of ARIMA model. There is another special case of model known as exponential smoothing models. Normally we don't consider these to be the typical econometrics or statistical model which are part of the ARIMA models, but it can be proved that the exponential smoothing models can also be considered as ARIMA model, some kind of an ARIMA model. So what happens in exponential smoothing model is it takes the average of last few observations. Okay, one of the reason why it's called exponential, because the assumption in this case is that the weight given to the recent observation will be more or higher than the weight given to the observations which are far away from the current observation. That means yt minus 1 will have a coefficient higher than yt minus 2 and yt minus 3 and so on. Okay, so in this case it's alpha 1 will be greater than alpha 2 is greater than alpha 3. Now if you compare this with AR model assumes that if let's say AR2 model, AR2 is there, and you have got yt minus 1 and yt minus 2. There is no guarantee that the coefficient of yt minus 1 is greater than the coefficient of yt minus 2. There is no constraint as such, but in exponential smoothing model this is a constraint imposed. It can also be shown mathematically that exponential smoothing models are also special cases of the ARIMA models. So ARIMA 011 with no AR component, only MA component, one or MA component, and one first difference is equivalent to exponential smoothing model. Will not get into the the derivation of that, but that just an additional information to what we have learned already. Okay, so that's about the theory behind ARIMA model. So in another video, we'll use some of the statistical softwares to build the AR, MA, ARMA, and ARIMA models by taking time series data. Could be a stock market data or stock index data, and then we'll do forecasting using these models. Okay, so we could use SAS, R, or Python to do that. Okay. Okay. The next point is, how do we identify the order of the differentiation? Okay, and that's an important thing. Okay, so the rule of rules of thumb is that if there is positive autocorrelation to higher lags, okay, and you're sure that there's higher autocorrelation till a lot of these lags. It's not just the first lag or second lag. Then you need higher order of differentiation. The first differentiation is not going to make it stationary. You need higher order of differentiation. And then when you have zero or negative autocorrelation, the first order itself, then no differentiation is needed. Okay, you be sure that it's pretty similar or is close to a stationary series. The important point is, what is the optimal order of differentiation? Okay, sometimes you will over differentiate, or sometimes you do under. You take under different order of difference is underestimated. So how do you deal with that? The optimal order of differentiation depends on at what order the prediction is closer to the actual value. Okay, so pretty much like any prediction model, we use some matrix to judge the predictive power of model. Like it could be a root mean square error, or mean absolute deviation, or mean absolute distance, or whatever. It's just that some sort of a distance between the actual values and the predicted value, right? When you take the sum of that or average of that, and the one which is providing us the minimum difference or minimum error is the best model. That's what most predictive models. That's how most predictive models are judged. Okay, so the one which is providing us the order of differentiating that is providing us the best prediction should be the optimal order. Okay. All right. So thank you so much, and please subscribe to our channel for more videos and new videos. Thank you so much. Please subscribe.